morning. Thank you, Dick, for the introduction. Thank you, ARC, for hosting us here and for Bentley for inviting us to this forum. I'm Sharad Oberoi. Welcome to the presentation today. It's called GIS to the Rescue, Geospatial Applications to Enable Smart Cities. So I'll first go over a quick company overview for those of you who are not familiar with the history of the Sanborn Map Company. I'll describe some general concepts about smart cities, go over some use case scenarios, basically categorized between mapping physical infrastructure, the human aspect, and communication between stakeholders, and then summarize. So Sanborn Map Company, if you're not familiar, is one of the oldest mapping companies still in business in the US. It was founded in 1866 by a Civil War surveyor, David Sanborn. He found out that at the time, the insurance companies required a lot of details on the interiors of buildings before they would insure them. So he started going out with a team of surveyors to map the interiors of every single building out there. It became such a lucrative business that the company started doing that for 12,000 cities across the US. These are some of the oldest known maps, the ones that we generated for most of the cities on the East Coast and the Midwest. And I can actually spend an entire day talking about it. We have since then evolved. We are now a full services geospatial data and solution provider. We have our own fleet of manned and unmanned aircraft. And we also have our own sensors. So we have something we call an orthoimagery sensor, which is a top-down imagery, the like you see in Google Maps. We also have oblique cameras. So in that, you don't just take the top of the building, you also take all the 4 cardinal directions. So that way, you can actually see the sides of the buildings. We have our own LiDAR systems, both aerial and terrestrial. And then we can also go to a customer and help them populate a geospatial database. So if an oil and gas company doesn't know where their assets are in the field, we can go in there, take an inventory, put them in a geodatabase, help them apply that to their applications, and do the full chain. We also do 3D modeling because all these pictures and all the data that we collect helps us extract value from what's out there. And finally, we are an ISO 9001 certified company. Our work culture, every single process is documented, repeatable, and we're really proud of that. This just gives a quick overview of what I was talking about. So on the top there, you can see we have our enterprise system assessment. So we would go to a customer, help them figure out in their enterprise what's missing. Since we have our own resources, we can then go ahead and start acquiring the data that they require, the kind of data we believe will meet their needs. Then we help them process the data. So it's not just stitching pretty pictures together. We call them photo maps. So each single pixel on an image that we take can be measured to get a value in the real world. So if I measure the side of a building in an oblique imagery, I can tell you exactly how tall that particular wall is. And that's being used by a couple of industries, insurance being one of them. So nowadays, you don't send somebody in the field to collect information about somebody's roof. They actually use our product. They just measure it on the online viewer, and they are done. And it's accurate between 1 to 2 pixels, which is like 3 to 6 inches. So it's pretty accurate, and that's good enough for their needs. Once we process the data, we also help the customer distribute it, because many of our stakeholders have people in the field. There are firefighters who sometimes, while going to the scene of a fire, they have to figure out what's the best way to approach. So on their tablet, on the way, they can pull up the oblique viewer and start strategizing even before they go on the field. So we have to make sure the data is accessible to the end user whenever they need it. Finally, we also help them maintain the data. So it's not just we come in this year and do it. We would come again and again till we actually are fulfilling a need that the customer has. And finally, this feeds back into the enterprise system again. So it completes the full data cycle, and that gives you an idea of the kind of stuff we work on. So smart cities. Geospatial technologies have been capturing the physical context of cities. And the idea these days with smart cities is that you can create virtual cities where the fusion of data can provide both physical security and a coordination between multiple agencies. If the different agencies know where the other ones are, they have a better perspective to approach a problem. This requires new forms of governance and public participation. So data, if you can convert it into information, and then you communicate it back to the stakeholders, they can then have a two-way communication. So your county government can not just tell you when construction is going to happen on your street, they can also ask you what might be a better time among multiple options. And that's the kind of stuff which, again, is not technologically savvy, but it contributes to the transparent governance. City models that we generate they constituted of multiple stakeholders. So obviously there's multiple data types that need to be integrated. It's not just the digital file formats, but also data coming in from sensors, data coming in from utility companies. Social media sometimes helps people figure out where diseases are spreading, things like that. This diversity makes the data and service integration very difficult, but there's also a value, because if we can get all the data on a common baseline, it helps not just from a functionality perspective, but also from the spatial interoperability. So how does GIS, the Geospatial Information System, play a role in it? A spatial data infrastructure is critical to create a framework so that the data, the smartness of the city is collected, coordinated, archived, and reviewed. A robust GIS will be able to generate this information and present trends and scenarios over time so that the implementation of the intelligent infrastructure can be accomplished. Populating the geospatial databases with real-time status and location from all your sensors, all your devices, can help with the running and upkeep of a smart city support infrastructure. So this is talking about the physical infrastructure, but there's also dynamic information laid on top. So I'll jump into the use case scenarios. The idea here is that each of these applications can be categorized into multiple broad categories. So I'm just speaking about the ones which are relevant from a geospatial perspective. And again here, I'm just handpicking a couple examples to give you an idea in the limited time that we have. So I'll first go over the physical infrastructure, and within that, I have each of these applications. I'll jump into them right away. So the first example is, how do you map static information? So in case of many modern cities, for example, New York City, the 3D building models that we generate, either from our photogrammetric techniques or LiDAR, we can actually generate a 3D wireframe. That building wireframe also has the orientation on where it's located in the city. So based on the sun angle at any given point of time, we can tell you how much solar potential that roof has. Utilities actually use this information. So in San Francisco, you may on your bill see at the bottom saying, if you install solar panels, this is the amount by which your bill will be reduced. And that's a good motivation to get people engaged. So we can generate that, and this data can also be published back throughout larger areas on an interactive website. Google right now has a project called Project Sunroof. So you can go in there, type in your address, and it shows your house in 3D and shows the solar potential. So this is an example from New York City. This is the LiDAR categorized by height, but each of these roofs, we actually have a potential assigned. So we can tell you how much money could be saved if they install solar panels. The next example is broadband mapping. So there was an initiative started by the Obama administration in 2009 called State Broadband Initiative Program. Under that program, FCC was mandated to talk to all the Comcast and AT&Ts and Verizons of the world and figure out which neighborhoods have availability of high-speed bandwidth. They had to not just find this out, but they had to publish the non-confidential data so that people could review it when they're moving, buying property, or county governments could review it to figure out if the lack of certain infrastructure is causing a lack of growth in that area. So we did this for Washington State, Oregon State, a bunch of other areas, but this just gets you an idea of the level of detail we can capture. No smart city can be designed or planned if you don't know what the land use or land cover is doing. So understanding this current land cover, how it is being used over time, can help people better analyze what's out there and how they can utilize it. Measuring the current conditions and how they are changing can tell you about the underlying trends. For example, if you figure out that the amount of forested area in your city is decreasing, that could be a sign of something else going on underneath. So once you can figure these things out, you can use remotely sensed imagery to extract these values automatically and use that to provide information. This is an example showing the different categories. It's not just showing that it's a built structure versus a forest structure. For places like the USDA, the Forestry Department, we can even tell you the type of trees there are. We also can capture the signature from diseased trees. So if there is a termite problem or something which is going unnoticed, we can warn you upfront beforehand. Impervious surface mapping is something which is also becoming popular. As we know, the impervious surfaces, the paved surfaces, the concrete surfaces in different households, they generate runoff that creates increased flooding, and they contribute more water towards the stormwater management system. So in many communities, an accurate assessment of the paved surfaces, the impervious surfaces, is required, because then that is added as an extra tax on your utility bill. So if you have an unpaved parcel in most cities in California, you get a normal bill. If you have it entirely paved, you have to pay a fine. So the way we do that is because we have multiple ways of collecting data. The red areas in here are the unpaved surfaces, so it's like a greenery and unpaved ground. All the grays are the ones which are the built areas. We can extract this by using semi-automated classification techniques, and this actually provides value to cities. This is an example for our mobile mapping. So in mobile mapping, what we have is basically a van driving around with a LiDAR on the back. That LiDAR is really high density, so it can collect up to 50,000 points per second. This kind of an application is used by departments of transportation to figure out if there's any cracks in the pavements, to take inventory of their assets, to digitize their assets. So once we have that, we can extract the terrain out of it. In this case, this was a utility example. So you see all the poles there, all the traffic lights, all the traffic light wires. They can be calculated and shown to the stakeholders in a real-time fashion. This has been around for a while, but it has certainly become a really interesting example recently with the advent of self-driving cars. So normally, when you have a GPS in your car, it contains the center line of the road. So it can tell you which road you are in, but it can't quite tell you which lane you are in. So for a self-driving car, it is important to know whether it's in the middle lane or the left lane, because that could make a difference in what decisions it takes. So we are building what we call HD maps. These are high-definition maps. These maps don't just contain the center line of the road. They contain the exact extent of the pavement. They contain information like, is there a median? Is the median raised? Is there just a yellow line? Is the shoulder drivable in case of an emergency? Is there an accurate XYZ location for all the stop signs, all the traffic lights? The idea is that in case of an emergency maneuver, the car going at 70 miles an hour should know in advance what's in the surroundings. So again, the idea was that the mobile mapping was being used by DOTs for many, many years, but now the same technology can actually be adapted for a newer application. Planimetric feature extraction. So what I showed as an example there was how you can digitize assets from LiDAR, but you can also do that for most geographic features on the Earth's surface, both 2D and 3D, by using photogrammetric techniques and LiDAR. I'll just show you an example here. So what you're seeing here are the contour lines for each of the areas overlaid with the extent of the river there. We also have building footprints. We also have road pavement markings. All these information can be extracted automatically. So again, it's not just a pretty picture. You can extract value out of it. You can use that value from GIS to feed into your smart city 3D model or smart city system. This is an example for an oil and gas installation in the Middle East. In this case, we actually we collected the data. We could digitize all their major assets in their pipeline installations, but we also sent people to the ground to demarcate where exactly their walls and control systems were. So based on this, we could go back and populate a big geospatial database with like more than 1 million objects and how they're depending on each other. So that kind of a relative ideology, again, feeds into the sensors that can now use this information. Now they know where things are related to each other and run through multiple scenarios. So it helps people make decisions when it could be critical. Okay. Okay. Indoor mapping is another one of a cool example. So traditionally, Sanborn Maps had been doing indoor mapping by survey tapes, sending people to the field. Most of the industry right now, if you have a Google phone or if you have an iPhone, in the next 5 years, they will be able to not just navigate you outside, but also inside the buildings. The problem that we have is that many of these assets have not had updates documented for multiple years. There was a study by the GSA saying that up to 30 to 40% of their buildings, they don't know what the floor plans look like because people added cubicles, they removed cubicles, the original building plans were lost. So how do you tackle that problem? So what we did was we came up with this robot called Sanborn Platform for Indoor Mapping. This robot, actually, if you allow it inside a building, it has an onboard infrared sensor which can help it avoid obstacles. It can avoid people, furniture. It goes along on its own, and as it's going, it's scanning the environment in 3D. Because now we have a 3D model out of it, we can use that model to build a 3D representation of the surface. So this is what a 3D point cloud of the interior of the Broadmoor Hotel in Colorado Springs looks like. But now we can use information like this to start digitizing it. So this is our Sanborn building, a model in 3D. You can see each of the assets in here, each of the chairs, each of the monitors can be tagged back to an FMS. So if you have a facility management system in your smart city system, you can actually take it back there and tag it. And if you have sensors, they can similarly be co-located. So we can scan it, we can model it, now you can use it for information. This is another example. This is using what we call a gaming engine, Unity. And it kind of gives you a sort of like a video game idea of what can be done. So all the light effects and everything is being done in real time. This is a video, but it was done in real time. And it gives you an idea. You can, again, think about it. You can click on any of this, get the attributes about it. It makes things relatively easy to understand. This is another one of my favorite examples. So this again shows the Sanborn building, Colorado Springs. It has a 3D model, it has the terrain, it has the mountains. The idea here was to show that you can use not just the outside information, but also the inside. So if you double click on a building, it takes you there. This one is a church. You click on the building details, it describes what it is. You now double click on one of the apartments in the background, it takes you there. It updates to show this is an apartment building. So it's quite fun and interactive to play around with because it gives you a relative idea of how things are situated. You can also manipulate the environmental variables. So if you click on the environment and say, make it go from morning to evening, it changes the sky color. It doesn't show in this video, but when you do it night, it even turns on the street lights. So it's pretty fun to play with. You can change the strength of the winds. You can also change the direction of the winds. You can add rain. So rain clouds come in, there's rain happening. And interestingly enough, so if you turn off the rain, you'll see it takes away the clouds after a while, not immediately, to make it look more realistic. So now it's blue, green again. You can also go inside the building. So what I showed you earlier, you click on the Go Inside button. It's now taking you inside. At the bottom right, what you're seeing is a base map of what the building is. And this is, again, a gaming environment. So you can use your arrow keys, or in some cases, you can use a joystick. And you're walking through a building. Again, each of these entities in here, the cubicles, the chairs, the monitors that you're looking at, these are connected to a live database. So you can click on them, get information. And the best part is, from a real estate perspective or from a 911 scenario perspective, you can also use it for gaming situations. So you can see from the inside out. And again, this can be done for any building out there. So it gives you a better idea of what's possible. Okay, so moving on to dynamic information. What can you do with 3D analytics? So geospatial technologies can capture the physical context of cities and create virtual 3D cities to facilitate decision making. We have seen that. But interactive 3D maps can be used as a visual way to communicate information which could otherwise be lost in translation. An example would be something like this. This is from the City of London. This is a demographic distribution. So the way they did this is they had the building footprints, and each of the height of each of the buildings here represents what demographic is the majority there. So you can see relatively which building is taller than the other. It gives you an idea of which demographic is more dominant one place versus the other. The different colors, again, represent different demographic groups. So it gives you a visual idea of what can be done. This is another example of the atmospheric emissions across London. And again, this is connected to a live database. So in real time, you could see these peaks going up and down and get a clearer picture of which part of the city is safer for a morning run than the other. This is the personal household energy consumption for Dallas. So they mapped each of the buildings with their per square foot energy consumption, and then they raised that to see which building is consuming more energy. Turns out some buildings are more notorious than the other. But if you color code that, you realize that it's because some of these buildings are really old. So they have really poor insulation. You may not have noticed that this building requires attention unless this kind of a graphic is put in front of you. So there are multiple ways to communicate information using GIS here. In urban planning, there's a very interesting use case where cities have started to accept 3D models of proposed buildings at the design stage and also at the as-built stage. These 3D models are then automatically validated to make sure they don't violate any zoning codes. So an example here is, this is from a company called Flux.io. What they did, this is an example for Austin, Texas. So you're seeing the Capitol building on the top left. There is a requirement in the zoning code there that no building should be taller than the Capitol building in a certain distance. So you can see there's like a parallel horizontal plane going on from there. There are also some trees which are considered historical trees. They cannot be cut. So as an architect, as a developer, if I have access to a tool like this, I can then figure out what's the 3D space that I have to play with. And this can also be done subground. So if you have any utilities where you cannot put in foundation without disrupting services, you can plan that in advance. And these kinds of applications, again, show you the potential of how GIS can help. Chain detection analysis is another big one. So many counties, they assess extra tax if somebody builds more on their property, but they have to keep track of people's honesty to report that and pay the extra money. Most people don't do that. So what we can do is we can collect the imagery at a regular interval, and we can compare the imagery on top of the other. So on the left side is an older picture, the right side, the same building, a newer picture. They've added a patio, and they've never reported it. So the system in the back end, it's generating a 3D model. We call it a DEM, digital elevation model, and it's subtracting the two. And automatically, anything like this just stands out, because even though it's not noticeable to the naked eye, the system can figure it out based on the elevation it finds. Volumetric calculations. So many situations, they have been the mining companies, construction companies, who want to keep track of how much progress they are making. This can be done using either LiDAR or photogrammetry, using manned aircraft or UAVs. But an example here would be, this is a stockpile example for a mining area. So on the top, you can see they had a difference on how much they had dug out. Bottom, they have a newer dig. Automatically, within a week of the collection, we can give them information back saying how much have they hauled out. And then they can compare that with their records to make sure how much leakage they're having, how much wastage is happening on the ground. And finally, the smart water network. So every utility, anytime, so it could be a water utility, it could be electric utility, anytime they gather or treat or distribute their resource, they're also generating and distributing data. The challenge is to transform this massive amount of data into meaningful information and transfer it quickly and accurately throughout the utility to all functions, so everybody is on board. An example here would be if you have a particular pipeline showing way more usage on a given day than it would otherwise do based on historical trends. You can have a rule in there which would automatically flag it out, and you can either look closely if the sensor has failed or send somebody to the field because this could be a sign of a leakage. So again, this is more proactive compared to a reactive response. I'll move on to the human infrastructure. The other two are really small, be assured. There's two main applications I want to talk about. There's a security application. We developed something known as Prism 4D. It is our real-time decision support and visualization software that has been used by many 911 and police agencies across the world. What it does, it provides an integrated command center operation with a single turnkey solution. So the entire city's police force, cop cars can be tracked in 3D. You can look at where they are. You can do scenario analysis, threat domes, and whatnot. The system is designed as a multi-pane interface to provide a common operating picture. So an example would be this. So on the top left, what you're seeing are different details you can pull up. So you can see, I want to see all the cameras, I want to see all the cop cars, whatever you want to see. In the center is a 3D representation. At the bottom is a corresponding 2D GIS, and the right side is a live video feed. An example would be this video. This is something we did for the city of Denver. So the scenario here is that there's a siege at the city county office. So somebody has just called in. So now they're pulling up the city county office, and now they have a threat dome. So that threat dome now means that any car, any person, any aircraft going through that dome has to be either restricted or monitored. So once they do that, now they're going to turn on the individual cameras. So these are the individual, they've closed down the roads here to make sure there's no through traffic. This is what they can see from their line of sight. So a person on the ground can tell what's a blind spot for a 911 person inside the county office. They can also do sniper scenarios. So these are the cop cars going by the way. So you can track them in real time. And this is a sniper. So the sniper can basically see what's visible. So they can figure out which buildings they need to shut off if there's a sniper threat. So again, this may not look that relevant right away, but for the G20 summit in Pittsburgh, they had to do something like this, and they used a similar tool. Okay. GIS solutions for individual population groups. So I'm talking about the elderly population here, but it could apply equally to other demographic groups. The idea is that due to a growing number of elderly people across the world, it's a necessity to create the cities that accommodate their needs, that keep them active, so that for every single hospital visit, they don't have to cross town in the middle of rush hour. So urban communities of elderly people can be offered services and tools to keep them active and to ensure that their primary needs are met. But the same thing could be said about childcare. So all your child services are in one side of the city versus the other. Finally, the communication between stakeholders. So we have a product we called Sanborn Web Gis. What it is, it's a two-way communication tool for counties. So the example I gave earlier about a construction happening in your neighborhood and you giving feedback, that's something which we can accomplish using something like this. It can be hosted by us, it can be hosted in the cloud, it can be hosted by the customer. There are multiple ways to do it. You can literally load any data layer that you may have which has a geospatial aspect to it. So if you have a parcel layer, street layer, city limits, we can load that. Utilities, zoning loans, stuff like that. So this is an example for the city of Portland in Texas. What you're seeing there in green are the building footprints. The blue ones are individual water lines. And you can see they also have the 6-inch or 16-inch, so you can tell how big a utility line is compared to the other. There are also the zoning codes in there. That's the fire zoning codes in different colors. So at a quick glance, people can see what's out there. The biggest application we have seen of something like this, even now, without a smart city, is people want to verify their parcel boundaries. So whatever the city has, earlier they had to go file an application. Now they can come to this tool, basically bring up Google imagery, overlay their house, and see what in the county records it say is their parcel boundary. In many cases, it has made the process more efficient. In others, it has caused litigation. So take your pick on that. We also have a 3D mesh. So large-scale meshes are basically a 3D model, which is an automatically generated 3D model is what we call it. So whenever we collect an oblique imagery, so it's the top of the building and all four sides, we can then use that inside a software like the one Bentley offers, Context Capture, and generate a 3D mesh. Once we have generated that, it could either be hosted locally or we can generate multiple levels of detail. So at a given zoom level, you only load what's relevant to you. And then this could be displayed over the browser. This can allow the similar kind of analysis to what I showed earlier for the Prism 4D, because now instead of having to hand model every building, I have the entire city, every tree, every house modeled automatically. Example here would be for Santa Clara, you could have the NVIDIA campus shown up. So what does it look like? This is a 3D mesh for Santa Clara, for a zoomed out view. If you zoom in, you can notice there's like houses in there, Target and a couple of office buildings, under construction building, apartment buildings, office buildings, warehouses, golf courses, and more office buildings. The idea again here is it gives a very realistic picture. And by the way, if you have noticed, if you zoom in too much nowadays with Google Maps, for many cities it switches to a mesh because it gives a better representation instead of just having a 2D view at a high zoom level. So this is a quick video I wanted to play. This describes the context capture. Let's listen a minute.
Context capture is Bentley's reality modeling solution that can quickly produce 3D engineering-ready reality meshes using simple photos and/or point clouds to provide real-world context for all types of infrastructure projects throughout the world. Fully scalable and versatile, context capture can be applied to many types of assets at different scales and uses a variety of sensors from laser scanners to handheld cameras or smartphones to produce precise reality meshes affordably with less investment of time and resources. You can combine aerial and ground-based photos to produce an accurate 3D model of your assets, whether it be an industrial site or an entire city. Using simple photos, context capture employs automatic area triangulation, 3D reconstruction, texture mapping, and reconstruction constraints to generate highly detailed 3D reality meshes, point clouds, and orthophotos.
Okay, finally, summary. What I've been trying to communicate here is the common feature among all smart solutions is that they empower the stakeholders by promoting their transparent communication. Collectively, better informed decision-making, both by citizens and the planners, improves the financial, environmental, and social outcomes for everyone involved. Smart cities have the potential to revolutionize the understanding of the environment. So we should keep the discussion going, and I look forward to your question during the panel discussion. Thank you.